So when you talk about trigonometry, what most of us are pretty familiar and I hope comfortable with is this idea of right triangle trigonometry. The ratios of sides that represent sine and cosine and tangent, and even our weird ones, the cosecant, the secant, the cotangent. And it's just all about the sides of the triangle with respect to whichever angle we're talking about. The problem with right triangle trigonometry is that it's limited. We can only talk about trigonometry of acute angles when we talk about right triangles, right? Because this one has to be 90. And so these two have to add up to 90, meaning each one of them has to be less than 90. So when we talk about, oh, look, here's the angle that we want, and let's do our SOHCAHTOA and blah, 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 we're only ever doing the trig of acute angles, which is a great place to start. But we're big boys and girls now. We need to be able to go beyond that. Okay? So, when we talk about trigonometry, we have to be able to expand on this idea of what we can do with acute angles to all kinds of angles, which is why this lesson is called Trig of Any Angle. And in order to be able to do that, we have to start thinking about our angles not as where two sides of a triangle meet, but we have to start thinking about it in terms of rotation around a circle. Okay? And if we do that, we can then expand beyond our acute angles into all different kinds of angles. So, a little bit of quick vocabulary to make sure that you remember some of this. Your angles have two sides to them. Angles are made up of two rays. They meet at a point where your endpoints of your rays are, which we call a vertex. Okay? Well, when we do this in a rotational kind of way, our vertex is always going to be right there, at the center of the circle that we're rotating around. And then our sides actually have names to them. So we have the initial side, which is literally where we start with the rotation. So it's going to just look like a single ray. And then it's from there that we start rotating around the circle to create whatever angle size we want. And wherever this other side ends up is going to be our terminal side. Okay? Now when we talk about this idea of angles in rotation form, we usually talk about them in standard form. And what that means is that if our angle is in standard form, it means the initial side is on the positive x-axis. So you can see here with our graph, and you have papers in your baskets on your table that have a similar kind of graph on it. We have this graph where we've got the circles, which indicates we're doing this rotation, but you also see these lines that kind of look like axes to us, right? And that's not a coincidence. We sort of put the two ideas together. We take this idea of having x and y axes, and we sort of fuse that in with this idea of these circles that we're going to rotate around. Okay? And so our standard form means that my initial side is going to start right here every time on the positive x-axis, and then I'm going to rotate from that position. if I rotate counterclockwise, then we're talking about a positive angle. And if I rotate clockwise, then we're talking about a negative angle. Okay, so if from here I decide to start rotating my side in this direction, not that direction, that's not what I wanted, in this direction until I decide to end somewhere, where I end is my terminal side. And this is the angle that I've created. Okay, look familiar? Okay. Coterminal angles mean exactly what they say. They are two angles whose terminal sides end up in the same place. Okay. So for example, if this is the angle that I'm talking about, and I ask you what is a coterminal angle, one possibility would be to look at the negative angle that ends in the same exact place. That would be coterminal. Another possibility would be to rotate around the circle several times and end up in that same place. However many degrees or radians I went through in all those rotations, that angle is still coterminal to that original blue angle because the terminal side ended up in the same place. Okay? Any questions about that vocabulary? Because we'll use it quite a bit, so I just want to make sure that everybody's clear. Yeah? Remember that? All right, so if we have this idea of rotating around a circle, then we need to think about how we measure that. The two most common ways to measure it are in degrees and radians. Okay? So when we're talking about degrees, all the way around the circle is how much? 360. So that means halfway around the circle is 180. And then our vertical axes, positive y-axis is how much? 90. And the negative? 270. So those are kind of the, I don't know, the place markers along the circle. You got 0, 90, 180, 270, and then back to 360. That's one rotation around our circle in degree measure. But then we also have radians. Anybody know what a radian actually is?
Isn't it the circumference? Like, doesn't it? It's around the circumference.
It's a unit angle equal to an angle at the center of a circle whose arc is equal in length to the radius.
Okay, now translate that. Tell me what that means.
Totally.
So is it like the angle that's equivalent to the arc length? Like,
yeah.
Yes.
So, if I take this, which doesn't quite fit all the way out here, so let's just use this circle as my circle for a second. So I'm going to use this circle as my circle for just a second. And I'm going to try to trace it as best I can. There we go. All right, so if I measure my radius for that circle, just a little bit long, so I'm going to... Okay, everybody agree? That's my radius? Okay. If I take that distance And now follow it along the circle as the arc. My whiteboard's too slippery. This won't stick very well. Right? You get the idea? The angle that you need to be able to cut off that much arc, that's how much a radian is. So radian comes from radius, because you're taking whatever distance your radius is, you are putting that along the arc of the circle itself, and you're saying whatever angle it takes to create that much arc, that angle is 1 radian. Make sense? Okay. So that's actually the definition of what a radian is. It's the angle that's needed in order to make the arc length on the circle be equal to the radius of your circle. And it doesn't matter what your radius is. Like I could have done this for this circle, in here, and it still would have been the same. So if I had taken that distance now as my radius, and then laid that on my circle, the angle would still be the same amount. Okay? The other thing that's nice then about using radians is that because we're talking about 1 radian being the arc length over the radius, right? This is how we, so the arc length, which is denoted by S, divided by the radius. Because they're both distances, so if that was in centimeters, then this would be in centimeters. If that was in inches, then this would be in inches. If this was in feet, that would be in feet. So because they're both measured in the same units, when we divide them, the units cancel out. And so radians are actually a unitless measure, which is why in calculus and in physics and things like that, where units matter, radians is the measurement of choice. If we use degrees, then we have to deal with that unit of degrees as we work out the problem. But if we use radians, then the units are not an issue because they technically are unitless. Okay? So, how many radians are in a whole circle? 2 pi. So in a half circle, excuse me, pi. The positive vertical axis is pi over 2, and the negative vertical axis is 3 pi over 2. Excuse me. Okay? So let's stop for a second and think about some of what we've just been talking about. Take a second and figure out one positive and one negative coterminal angle for each of these angle measurements. Your clue to this is to be consistent. So if I'm giving you a degree measurement, you give me degree measurements for answers. If I'm giving you a radian measurement, you give me radian measurements for answers. Okay? So one positive and one negative coterminal angle for each of those. Elijah, got an idea for 140 degrees?
Yeah.
Okay.
The positive one would be 500.
Would be what?
500.
500?
Negative 43.
Okay, so how'd you come up with those answers?
Oh wait, it's not negative 40.
It's negative.
Negative 120.
Yeah, it's 220.
220?
Negative
Yeah.
220.
Negative.
Okay, so how'd you come up with these?
Uh,
How'd you come up with 500?
you add 360 and then minus 360.
Alright, so basically what we're saying here is in a rotation, about where is 140?
At the second quadrant.
Over here in the second quadrant somewhere. So we're over here somewhere, right? That's 140 degrees. So if I need another angle that ends up in that same place, one way to get there is to keep going this way around the circle until I come back to it again. Well, how many degrees did I just rotate through? 360, right? I just went all the way around the circle one more time. So if I take my 140 and add 360, then that gets me the 500 answer. But another way that I can get there is to actually say, okay, so let's start here and let's go negative. Let's go clockwise to get to that same spot. Well, in order to figure out how far you went, you're basically saying, well, the whole circle is 360, so let's subtract the 140 from it to figure out how much more I have left for that one. But if you set it up as negative 360, taking your 140 and subtracting 360 from it, then you get the negative as part of your answer, and that's what you wanted, was a negative answer. So the 140 minus 360 gives us the negative 220, the 140 plus 360 gives us the 500. Make sense? Okay, how about our 7 pi over 5? Cindy, first of all, tell me where that is. Sorry? Okay, I just want you to tell me though, which quadrant do you think 7 pi over 5 would be in? Let's start with that. Which one? Third quadrant, yep. Because this is a little bit more than 1, right? 5 pi over 5 would be 1 pi, and we know that's halfway around. But it's not hugely more. It's not like we're almost to 2 pi. So a good guess is probably that we're talking about something over here in the third quadrant. Right? So 7 pi over 5 having gone this way around to get there. All right, so what should I do to get another positive angle? Casey, what seems like a logical choice for getting a positive angle? Look at what we did over here.
If you add like 2 pi to it.
Exactly. Okay, but we have to maybe tweak this just a little bit because we're talking about fractions now, right? So what do we need when we have fractions?
Common denominator.
A common denominator. So how can I rewrite 2 pi to have a common denominator so my adding's easier?
10 pi over 5.
10 pi over 5. So instead of writing it as 2 pi, I'm going to write it as 10 pi over 5, which is equivalent, but gives me the denominator I need. And so then I end up with an answer of 17 pi over 5. So that would be a really good positive choice. What would I do for negative?
You subtract.
Yeah, we're just going to subtract the 10 pi. Whoops. Yeah. So 10 pi over 5. So if I take 7 pi over 5 minus 10 pi over 5, then we get negative 3 pi over 5. So there's your positive and your negative. Okay? Questions on that? Everyone understand now what we're talking about when you're asked for a coterminal angle? Okay. How about conversions? So what do we know about degrees and radians that are equivalent?
360 degrees is 3 pi. 180 degrees is pi. 90 degrees is pi over 4. And 270 is 3 pi over 2. Or pi over 2.
You lost me after that. Which other ones did you say?
I said 270 is 3 pi over 2.
Now, one of the things we have to be really careful about, because radians are unitless, we don't need to write anything after it. If you want to, for emphasis, you can put RAD to say that it's radians. But we assume that if there's no units listed, it must be a radian measure. Which means that when we're talking about degrees, we have to remember to use degree symbols. Because if there's nothing there, we assume we must be talking about radians. So anytime you're asked for something where you have to give a degree answer, make sure that you are using the degree symbol after it to indicate that. Write yourself a note, highlight it, circle it, put stars around it, whatever you have to do. Make sure you're putting that degree symbol there or it's going to be counted wrong. Okay? All right, so lots of different equivalencies. Which one looks like the easiest one to work with?
360 and 180.
That one's pretty simple, right? 180 degrees pi radians. So that's what we use when we're trying to do conversions. If I'm trying to go from degrees to radians, okay, then I need to take my degree answer, the measurement I'm given, multiply it by something to make it into a radian answer. Well, radian answers generally have pi's in them. Not always, but often. And so I'm going to take this idea of 180 being equal to pi, and I'm going to divide both sides by 180. Which means that 1 degree now has to be pi over 180. So however many degrees I have, if I multiply that by pi over 180, that'll convert it into radians for me. Vice versa, if I'm trying to go from radians to degrees, then that means that I started probably with something that had a pi in it, and I now need to change that into degrees. So now I'm going to divide the other way. I'm going to figure out what would 1 radian be equal to. so that I can multiply that by the number of radians I'm given. So if I'm trying to go from radians to degrees, then I multiply everything by 180 over pi. And what's nice about that is our pi should then cancel out, and we'll just get something numerical that makes sense as a degree measure. All right, so using that, convert those two real quick. Everybody got those written down? Because I need to open up my calculator really quick. So you have the 220 and the 11 pi over 8 written down. So if you don't see it in the next few seconds, it's not a big deal. All right, Rohit, tell me what to do for 220 degrees.
You multiply it by pi over 180.
Then what?
You divide 220 by 180, which is 11 over 9. You simplify sign to 11 over 9. Then you add the pi, so 11 over 5.
Okay, so once you set up the multiplication, simplify. I can divide them both by 10, that's easy enough. I can divide 22 and 18 both by 2, so that gives me 11 here, gives me 9 here, and so I end up with 11 pi over 9. We want to keep these in fraction form. Okay, so just simplify as much as you can, and then 11 pi over 9 is the type of answer we're looking for. Okay? Olivia, what do we do with 11 pi over 8?
Take that and times it by 180.
Okay, so what can I do with that?
So and then we do 1,980 pi over 8 pi, and then you simplify that
Oh wow, you did the hard way. Can someone give her a suggestion of what might be easier?
Cancel out the pi's.
Cancel out pi's. No more pi.
And then simplify 180 and 8.
Yeah, simplify here. Make that a little smaller before you have to multiply that all out. Because a lot of times this kind of problem is not going to be on a calculator section. So help yourself out. So what can I divide them both by?
4.
A 4. So that's going to be 2. What's 180 divided by 4? 45. Is that down as much as we can do?
Yeah, 465.
Okay. And do you all know the trick for multiplying by 11?
Yeah, I do. What's the trick?
It's awesome.
You
Go 40. Whoops. That doesn't work on there. Go 45 times 11. Right? Take the two digits you're multiplying the 11 by, split them, add them up. $4.95. If you add them up and you get something more than 10, then you just do the carryover like you would with any other adding. Yeah, pretty cool.
Wait,
That's how it works.
Go ahead, tell me I'm wrong. Go ahead.
no, I'm not, I'm absolutely not gonna tell you you're wrong. That's not what I was going for.
It works because
So
what do you do when you actually multiply? You end up taking 1 times 45 and then 1 times 45 but shift it over.
Really adding.
So all you end up doing is taking the first digit plus the second digit in that middle,
Actually, wow.
right? All right, so we end up with, what do you say, 495 over 2. And then that's easy to divide, right? Like I can divide anything by 2. So that's going to be 2, 4, 7.5 degrees. Okay, make sense? All right, now there's another little bit of conversion we need to be aware of. We're not going to do it a lot, but we're going to see it now and then. And it's sort of a subset of the degree category. And it's called DMS. DMS stands for degree minutes seconds. It is generally used when you're talking about navigation, directions, latitude and longitude, that kind of stuff, because it allows you to get more precise than just a degree. So if you see one tick mark, a single tick mark stands for minutes, and there are 60 minutes in 1 degree. And then the double tick mark, let's try that again.
What's the one tick mark?
Minutes. 1 tick mark is minutes. The double tick mark is seconds. There are 60 seconds in a minute, just like you would expect, which means there's 3,600 seconds in a degree. Okay? So when you see something written like this, it means 48 degrees, 20 minutes, and 50 seconds. Not as a time, but as an angle measure, a very precise angle measure. Okay? And sometimes we don't want it in that DMS form. We want it in just a regular decimal degree kind of form to work with. So, you can convert these on your calculator. So I want to show you really quick how to enter a DMS equation or measurement. So 48 degrees. Degrees is actually in 2 different places. That's fairly easy to find. One is this pi button that's over here by H, and the other one is this punctuation button that's over here by G. Okay? Doesn't really matter which one you use, but you want the degree symbol. Okay? And then for, how many minutes did I have? 20 minutes. So 20, go to the same place, either one, and you choose the tick mark. So it's kind of nice in the punctuation button because they're right beside each other. Okay? If you do it here on the pi button, you've got degrees here, and then you've got the tick mark over here. So, I mean, they're both there. It's just a little nicer in the punctuation one. Okay? And then for our, what do we have, 50 seconds? This one's a little bit cumbersome, but at least you can do it. You type your 50, you go to your punctuation, you choose your tick mark, and then you go to your punctuation and you choose your tick mark again. So you get your seconds.
Whoa.
Okay? And so now when you hit enter, if you're in exact mode, it's probably going to give it to you as a fraction. So if you do your control enter, you'll get it as a decimal.
How do you do double tick marks? Oh,
You just have to go to that menu and do it twice. Yeah, there is no double tick mark. Don't be fooled. Some of you may have tried this. If you go into the punctuation, it's like, oh, look, double tick marks. It's not. It's quotes. If you click on that, you'll get quotes with an empty box. Like, what do you want to put in quotes? So that is not the second sign. All right? That's quotes. So you have to use the tick mark that's up there by between the degree and the percent sign. You just have to go and do that twice to get your seconds. Okay? So 48.3472 is what we end up with. So 48.3872, is that what I said?
3472.
3472. I want to say something about that didn't sound quite right. Okay, now to go the other way, there are times where I'm given something as a decimal, but I need it to be in DMS form. So 130.75. I type my 130.75, and then I have to go to the book. The book. It may be somewhere else, but I don't know. I do know it's in the book. Okay? So, when you open up the book, it's the catalog of everything your calculator can do. And once you open it up, it's probably going to start up there at the top at ABS. And you're like, are you kidding me? I have to scroll down through all these? No, you don't. If you type D, it will at least get you down to the D section. So you can skip scrolling through A through C. All right? Now you have to scroll, excuse me, through the D's. And there is a command right there. So it's a little triangle and then DMS, which means we're going to take whatever we typed in and we're going to convert it to DMS. Yes, it's mine this time. It's probably some telemarketer, so I don't care.
Which are the worst?
Okay? So this is the command to convert into DMS. So as soon as I hit enter, it's going to show up in the line for me. And then when I hit enter again, it will convert it. So 130.75 is the same as 130 degrees in 45 minutes. Okay? Yeah.
Wouldn't the change always be less than a degree?
Sorry?
For like DMS to degrees or like degrees to DMS, the change will always be less than a degree. Because
Yes.
Okay, yeah.
Yeah. So you should never go more than 60 minutes. You should never go more than 60 seconds because it would take you up to the next level in the DMS. So if you are starting out with something that's 130 point something, you're going to have 130 degrees. It's just a matter of what does the 0.75 convert into in terms of minutes and seconds. And vice versa. So the degree part should not change on you. It's just a matter of converting that decimal part, the partial part, there you go, back and forth into decimals or minutes and seconds. Okay, but you can do it on your calculator. So when you get to, there's a few problems like that in the homework, do them on your calculator. Okay, so we would write this as 130 degrees and 45 minutes. Make sense? Questions on being able to go either way? All right, let's take a quick break. Everybody out. Oh, stretch a little bit. This is the one I like, where you grab your wrist and just pull a little bit. It's your back crack.
Oh, yeah.
Oh no.
And grab your other wrist and pull a little bit. Listen to your back crack. Roll your shoulders, little.
I'll make a stretch at the end. I got home and
All right, let's get back to it. Talk a little bit about arc length and sector area. So because we're now talking about angles in terms of rotation, there's this connection with our angles and with circles, right? So a little bit of quick vocabulary with regard to circles. We have obviously a radius, which is anything from the center out to the circle. So the orange would represent a couple of radii on our circle. A central angle is any angle that has its vertex at the center. Okay. Arc length is any piece of the circle. So the green here represents an arc length. In this case, the arc length is being created, the arc is being created by the initial and terminal sides of our angle. And they use a big fancy word called subtended. So our arc is being subtended by the angle. It's just a fancy way of saying cut off. Okay? And then the space that's inside of the angle and within the circle is what we call the sector area. Okay? Be careful about the labels here. The A is for area, not for arc. We use an S for arc length. A represents sector area. So S is not for sector, A is not for arc. It's a little bit confusing, but just keep those straight. Okay? The other thing I just want to point out here really quick, because I don't think I said it before. A lot of times when we talk about angle measures, but we don't know what the actual measure is, mathematicians tend to use Greek letters as their variables for those rather than regular letters. They do also sometimes use capital letters to represent angles, but a lot of times you're going to see things like alpha, theta, beta, gamma. So if you've gone to visited a college and you've seen all the Greek letters on the fraternity and sorority sweatshirts, you're going to see them in math too. All right? Because they do use a lot of Greek letters as variables for unknown angle measures. So this is theta. Anyone's not aware of that. Theta is real common. Alpha, it's like that one, looks like a ribbon. You took the pink ribbon and put it on its side. Beta is like a bee with a tail. And gamma kind of looks like that. Okay? So it's like an upside down awareness ribbon. Alright, so if you see any of those, just know they're Greek letters and they're just variables representing unknown angles, just like any other variable would be. Okay? So, we talked just a second ago about the fact that the radian was S over R, and because they were meant to be the same, that meant you had a radian of 1. But what comes from that is an equation that works all the time. Your central angle is always the result of taking S divided by R. But you have to realize that this is an angle that is in radians. Okay? So what that means then is you can also use that in other forms. For example, we can multiply both sides by the R, and we can come up with the equation of S equals theta times R. So we can find arc length by taking the central angle measure times the radius, but again, as long as our angle is in radians. For sector area, we can derive from what we know about circles and how to find area of circles that we end up with a sector area equation that is 1/2 r squared theta. So it's kind of a combination of triangle and circle, if you look at it. And that's kind of what we've got going on, right? When we talk about sort of that wedge of pizza or that, piece of pie kind of situation, it's kind of this triangular part of a circle. And so it's interesting, I think, that our area formula is kind of a fusion of the two of those. We've got that 1/2 out there in front like we would with a triangle, but then we've got that r squared times theta. The r squared kind of comes from our circle, pi r squared. And we're going to take it times whatever theta is as a radian. Okay? So with that in mind, answer those two questions. How hard would you get for arc length?
I got 5 pi over 3.
Okay, and how'd you get it?
I put in pi over 3 times 5, so the central angle times the radius.
Pretty simple, because in this case, our central angle is being given to us as a radian, so it's just a matter of taking the radian times the radius, boom. If you are dealing with this kind of problem on a section where you can't use your calculator, then just leave it like this. Except we're missing one little thing. Inches. Yep, make sure you put a label on it. We're talking about the length of this part of the circle right here. If you're actually on a calculator section, you might be finding this as part of some application, real life kinds of problem, then go ahead to your calculator and work this out as a decimal. Okay? What about sector area? Ethan, what did you do to get sector area?
Pi over 3.
Say again, please.
25 pi over 3.
25 pi over what? 3? Okay, how'd you get that?
I found the arrow using the radius and pi by 6.
1/2. And it's 1/2 r squared times theta. So
So does that give me that? What do I need to fix?
It's 2 times 3 in the denominator. It's 6.
Yeah, so this should be 6 instead of 3. Otherwise, we're all right. We just need to make this a 6. Okay.
I knew that was the same as 1.5 pi.
All right. Let's try one more. Like that. All right, so Morgan, what's the first thing we have to do before we can answer any of these questions?
You have to change the angle to
Excellent. Yep. So in this case, we're being given our angle, but we're being given it in degrees. So the very first thing we need to do is change our degrees into radians. So what's that going to end up giving us? Say again?
5 pi over 18.
5 pi over
9.
9. Yeah.
Just kidding.
Divide both top and bottom by 0. Okay? So once you have that, then you should be able to find your radius. So what would our equation look like? Hagen, what would our equation look like?
R equals x over
Okay, so r is going to equal
10 over 5 pi.
how do I do with that?
Cancel out. Let's do 10
So 10 divided by 5/9 is the same as 10 times 9/5, which means I should be able to cancel there, and I end up with 18. There we go. 18 centimeters. Okay? How about for our area, Zeb?
So it's 18 squared, which is 824 divided by 2 times
Times what? Theta, and what's our theta?
which is 100 degrees, so 100 times pi over 8
So that's saying 5 pi over 9. Okay? Now, watch this little trick. What do I end up with for my denominator? An 18.
Wow.
end up with 18 pi. And it's 18 pi what?
Okay, what happened?
What happened to the 5?
There's a 5 pi.
Oh, fine. Put 5 in there too if you want to. All right. All right, so instead of 18 pi, it should be
5 times 18.
90 pi.
No, I was like
90 pi what?
inches squared.
CM
Centimeter squared.
Sounded so
Make
sure.
sure you're squaring it because we're talking about area now. Okay, but it's centimeters squared because based on this. Okay, we're going to this one next because I'm pretty proud I can set this up. So we're gonna do it.
That's very sweet.
All right, so I'm gonna slow this down here. I'm gonna stop this for just a second. So I get my pointer here.
Fly off the top. They did show off these ones.
Oh, they're so fast.
Okay, so what we've got going on here is a model Ferris wheel. Okay, and I have overlaid it with a circular compass, right? So that we can see what kind of rotation we're talking about and that kind of stuff. When we talk about things that are rotating like this, going around in a circle, there are two different kinds of speed that we can talk about. Anybody know what they are?
Rotational. No. Linear and angular.
Yeah. So rotational speed would be angular speed, and then linear speed. So for linear speed, we're trying to find distance over time. Okay, or maybe we should say change in distance over time. Change in time. You all know the delta, right? Okay. For angular speed, we're looking for the change of the angle over the change in time. Okay, so one's looking at actual, if I'm looking at a car out here on the edge, how far has it actually traveled in a certain amount of time? That's linear speed. Okay, but if I'm looking at how much has the angle rotated through in a certain amount of time, then that's angular speed. Both of them can be useful. Both of them are sometimes necessary depending on the type of problem you're looking at. So we need to realize that there is this difference, and we need to think about how am I going to set this up? How am I going to figure this out? So what I would like us to do, we got a couple minutes yet. I want us to figure out the linear speed of one of the cars out here on our Ferris wheel once I set it in rotation. Okay? And what I'm going to do is I'm going to set the clock to start counting off, and then I'm going to set the Ferris wheel to start rotating. And within your groups, at your table of 3 or 4, I want someone to be the person who's going to watch the Ferris wheel, and you're going to pick one of these cars, and when it hits 0, say go. And someone else in your group needs to be watching the clock.
I got this, guys.
So when your Ferris wheel person, says go, your clock watching person says what the time is. Okay? Ferris wheel person, don't take your eyes off the Ferris wheel. Follow your car all the way around the circle. And when you get back up here to 0, say stop. And clock person, say what the time is. A third person in your group should be writing those down. What's the start time they said? What's the stop time they said? Okay? So one person is watching the car, one person is watching the clock, and one person's going to write down what the clock person says.
You'll watch the clock.
Okay?
I'll watch the Ferris.
That way you
I'll just write
can
down what.
decide the distance. Or sorry, you can decide the time that it takes.
I mean, I got
Make sense? Any questions on what we're doing?
Why is it right there?
No, there's a lot of blue ones.
Don't do anything.
Don't
do it. Don't do
That's
it.
retarded.
Because if we screw up, then we'll have to like
There we
subtract
go.
numbers. Time.
Okay, I'll tell you when this is not right.
Alright, so whenever you run out of
Too
time.
fast, I can't follow.
Too fast?
Yeah.
Alright, slow down a little
Okay,
bit.
pick one.
It doesn't matter, just pick
Start
time.
20. Start
Alright,
20.
don't have a-
Okay, start.
Go.
But you already started.
If that's still my first wheel, I don't even know.
No one has time to start
You're
it.
not my first. Stop. Stop.
Which one are you looking at?
I don't know. You're looking at the clock.
But I wasn't even sure if I would be very hard for it. Like,
Everybody got a
It's
time?
not done yet?
yeah.
Wow. How?
It
It
went
was
through
like 4
two times. One time around the circle.
Okay, let's restart. Ready?
No.
At 60 seconds.
Okay, at 60 seconds start. A minute. Choose a card. Choose a card.
Just choose any.
Okay, got a time.
At 1 minute.
I don't know why
Go.
they're making this so hard.
Bad at it.
Are you looking at the red one?
Looking at a blue one. Okay, that took like 10 seconds. Yeah.
So everybody got a time now?
10 seconds.
There's late.
Alright, back there, Steven's group. What'd you get for time? 9, 10, 10, 10, how much?
You messed up.
10, 10, okay. So everybody comfortable with going to 10?
18 seconds.
9 is probably just a matter of like, where you at? 32.5 or 32.1 and like, yeah. So, okay. So we're gonna go with about 10 seconds. So the next question is, stop it. How far did your car travel in that amount of time? Okay, so here, and we're doing it actually for this model, not for an actual Ferris wheel at the moment. So let me get my.
Just the guitar.
There we go.
Just the guitar.
There we go. All right, so here's my ruler. Drag it down here so it's in line pretty much with my diameter, right about there. Okay. So we're going from there is the center to up there. About right? Okay. 4.6 centimeters. All right, 4.6 centimeters for that. And 10 seconds for our time. So, how far did your car travel?
No, it's 2. Oh, wait, 2.89.
Wait, and then what?
6.6
I didn't ask you that. I asked you how far did your car
Oh, wait.
travel?
I said 28.9 centimeters.
28.9? Everybody agree?
Hunter physics.
28.9 sound good?
Or we could force it to have to read.
Steven, is that right?
You like it? 28.9? It's all good? 28.9 what?
Centimeters.
Okay. What was our time?
10 seconds.
So based on that, what is our linear speed?
1.89.
Now, does that mean anything to anybody?
Yes.
Unreal. That's like
Maybe if I was in physics it would, but quite honestly, like,
velocity.
is that fast? Is that slow? Is it like?
It's actually
That'd be
pretty quick.
scary to be on.
So, let's do a quick, we're almost out of time. Let's do a quick conversion to something that makes sense. Change it to kilometers per hour. How do I do that?
Wait, what?
Divided by 3,600 to get it to
That's not
hours.
helping.
Into hours.
Just do the thing.
No, you multiply by 3,600 to get hours.
You've got to use your unit analysis. Okay? Unit analysis is how you set up your numbers based on the units to make sure that units are going to cancel out to give you the unit answer you want as well as the number answer you want. So because I have seconds on the bottom, give me just 2 seconds. Because I have seconds on the bottom, I need my 3,600 seconds that are in 1 hour. Set up like that, right? Because I need seconds across from seconds to cancel out. What about the distance? How many centimeters are in a kilometer?
What?
1,000.
It's 10,000.
1,000 meters in a kilometer.
100,000.
So 100,000. So where do I put the 100,000? Top or bottom? Bottom.
I just didn't get away.
I don't do physics. I don't need that.
So this is actually really slow. If you work this out, it's like hundredths of a kilometer per hour, or something like that, tenths of it. Less than 1, okay? All right, I highly recommend you do a little bit of that homework tonight based on what we've done. We'll finish things up on Thursday. See you then. I put your test in your folder, so if you want to take a look at it, it's back there, okay? So you need to do,
I did the homework.